At time now, so I will hand it off to you.
Awesome. All right. Well, thank you everybody for being here, for attending, and I'm very excited to be talking about security by design and what it means for APIs. So what we're going to do is we're going to see how our API designs can expose vulnerabilities, what those vulnerabilities look like, and how they can be exploited. And we're going to see how we can leverage design for security. So how we can use a spec as an artifact in our testing process to identify and tackle vulnerabilities in the APIs. The way we're going to do this is I'm going to start with a brief introduction about the current state of API security by looking at this from the perspective of API security by design. Then we're going to see what API security by design is. We're going to begin with a simple example of how a design can expose vulnerabilities in unintended ways. And then we're going to see how we can use some automation tools to scale the process of identifying and tackling vulnerabilities in our API designs. Before getting started, just to introduce myself, my name is Jose. I'm the founder of microapis.io, which is a company that I use to channel my consulting and training services. I'm the author of Microservice APIs, the book over here, which explains everything you need to know to design and build microservices and APIs. I'm the creator of Fensa, which is an open source API security testing tool. It's been dormant for a while, but I intend to resume work on this soon. Not very effective at the moment, just starting. And just recently, just a few days ago, we launched a new book, Secure APIs, which is all about how we tackle security from the developer and the architect point of view, because that's the background I come from as a developer and architect. And so the point of the book is to answer questions, to learn about categories of threats and such. But the point is to address the question of, and how do I protect my APIs against that? And that's the point of the talk also. If you want to grab a copy of the book, there is a one-time discount code here of 50%. So this is the best time to get it if you're interested. We won't have this kind of discount later on. If you're interested in my content, different links here. I believe you will have access to the slides later. So if you want to access my YouTube channel, my courses, newsletter, and such, all the links will be here. And just wanted to say, emphasize the point that the point here is to tackle security from the builder's perspective. So I hope this is like a good complement to Dana's talk, where we've learned everything about testing and looking at APIs from the attacker's point of view. I think now is the turn to look at them from the developer's point of view and how we address those vulnerabilities in our design and implementation. So what's the problem? The problem is that APIs are inescapable. If you're a developer, you probably have this situation. You're building a new component in your system or something like that. We have an API on the backend and an application on the front end consuming that API. We use APIs also to drive integrations between microservices, to enable partnerships with other businesses, or to deliver products and services directly through the API, as Stripe would do, for example. So that means most of the traffic, and especially most of the traffic that accesses business logic, goes through APIs. And that's a problem because we haven't really cracked API security very well. So if you look around APIs, like most of them have vulnerabilities in one way or another. And the number of data and security breaches that are happening due to APIs, the number of those breaches through APIs is growing. The most recent case, or one of the most recent, happened to Dell a few days ago. So it's a nearly 50 million user data breach involving personal details like names, physical addresses, customer order details, warranty information, and so on and so forth. Now, those details in isolation might not be very useful for an attack, but they can enable different forms of phishing scams and so on and so forth that can put our customers at stake. The problem here was in a Planet API, so an API that Dell was using to do business with business partners. And this is not an isolated case. A few years ago, a cybersecurity researcher found a similar problem in Toyota. So Toyota has a business partner API as well. And they found completely unauthenticated endpoints where you could access sensitive data from Toyota's business partners, exchange of messages containing business secrets and information like that. I've worked on a few business partner APIs myself as well. They tend to be not very well protected a lot of the time. So if you have that kind of API in your system, make sure they are adequately protected, because they can leak so much business and personal data. This is an example, a screenshot I took just an hour after deploying an AWS load balancer for a client. And so this is what happens. You deploy a service online, and within an hour of that deployment, you're getting an automatic profile of that service. So these are automated tools that are looking for open holes or vulnerabilities in the system, well-known endpoints that are well-known to contain sensitive information or configuration. In this case, it's fine. Everything is not found. But the moment something potentially sensitive is found, this information is passed to the threat actor behind these tools, and they can tailor and plan an attack strategy for our APIs and look for open holes in it. And I mentioned most APIs have some form of vulnerability, so we won't be in a very good position if that happens. Now, what's the deal here? Why are we in this critical situation with APIs? Part of the problem is that API security is difficult, and it's difficult because it's different from traditional web security. So if you have experience building websites with Ruby on Rails or Django for Python and similar frameworks, something you should notice is that those frameworks do a lot of heavy lifting to take care of security for your website. So they do things like including built-in user session management, login, they manage CSRF tokens, they include by default configuration for cores and things like that. When it comes to APIs, we are on our own. API frameworks don't give you this built-in protection, and part of the reason is because we need that flexibility. So it's on us to decide what are the business requirements to put together the right authentication and authorization flows, how to issue secure tokens and handle and validate them correctly. Make sure, for example, we are not sending ID tokens to our backend for validation. That happens. How we define robust models, data models that don't expose unnecessary data to our users, and also that allow us to apply robust validation in the backend to prevent things like mass assignment. So all of those things are on us. And that means we have to bake in security into our development process. Otherwise, we're going to be open to many different kinds of abuse and attacks against our websites. OWASP, the Open Worldwide Application Security Project, took notice of how different API security looks like from traditional web security, and they created a specific API security top 10 list in 2019. That was updated in 2023, completely revamped with new categories that are very specific to API security. Now, here we're going to focus on security by design, and also as a warning, we are going to look at some technical aspects of API design and implementation. I'm going to try to explain everything, but if you have any questions about anything I say, please put your questions on the chat. So by design, there's things we can do with automated tools. So this is an example of running Spectral, which is a popular API linter against an API. It has various rule sets, and one of them is the OWASP rule set. So you install that rule set, you enable it in Spectral, you run that against an API specification, and it will look for potential vulnerabilities. Now, the NatWest is a very popular bank in the UK, and in the UK and Europe, there is this normative to encourage banks to open their services through APIs. In the UK, that's in the context of open banking. So NatWest went far and beyond that requirement, and they created a whole brand of bank of APIs. And so they've done an excellent job. It's among the best APIs you can find in the fintech sector. And so Paid is one of the products they've created as part of this initiative. It's very well done, but even in something like this, we find nearly 500 potential problems in the API. And Spectral is going to be looking at things like unconstrained user input. So for example, free-form strings, unconstrained integers, and so on and so forth. Now, NatWest is very well done. This is more common. So Plate is a multi-billion valuation fintech startup. They have an API, and so I run Spectral against the API, and what we find is something more like this. So nearly 7,000 potential problems in the API. Of course, the bigger the API, the more problems we will find. So this is GitHub with nearly 55,000 potential problems, security-specific problems in the API. Now, a lot of these problems are on the surface of the API specification. They may be handled in the API implementation. So for example, we have an unconstrained integer that doesn't show up in the specification, but maybe it is handled in the implementation. The problem I find here is this drift between documentation and implementation is not helpful because it doesn't allow us to audit and assess the API properly from a security perspective. And we can't use this as a validation tool against the backend either. So as far as possible, the best situation is to reduce the drift between the implementation and the design so that we can use both tools as implementation and evaluation artifacts. Now, to give you an example of what vulnerable design looks like, this is an example of a pagination pattern. So pagination is the ability to slice a collection of items into smaller chunks so that we can process them more conveniently. And so this would be a get product endpoint. If you're familiar with the OpenAPI specification, this is what a specification would look like in that spec. So we have this endpoint with that operation, and we have a number of parameters here. So per page allows us to specify how many items per page we want to get. Page allows us to specify which page we want to look at, and we have other parameters to sort and filter the items in the list. Now, this is a perfectly fine and standard pagination pattern, but it is also vulnerable. The intended use is like this, right? User comes to the API, they get a list of products, they specify the page or the number of items per page, they filter by toasters and so on. But a threat actor may come around and they may say, well, what happens if I request 100 million items per page? You see, by design, there is no constraint here on how many items we can request. What's the value of that parameter? We can just as well put a negative value here. If the implementation is done exactly like this design, our API is vulnerable to these types of abuses. We can do the same with the page parameter. Something like a string, like the filter or the order parameters, are vulnerable here to SQL injection attacks. Now, this SQL injection won't work. I'm gonna show you one later that will work in this case if we don't have parameterization in the backend, in the implementation. But lack of constraints on those fields is going to open the door to SQL injection attacks and other forms of abuse. Now, in some cases, this is perfectly fine by design. We can't put constraints on certain values. But when possible, it's better to put constraints in place so that users can't, play around with the API and abuse it. So to address these problems, we try to put security into every stage of the API development process, beginning with the design. Ideally, the API development process begins with design. So we start thinking about what we want to do with the API, what kind of operations and flows we want to expose, what do the data models look like, the models we have to exchange in every operation. And as we're thinking through that, this is a perfect stage to start thinking about what are the possible threat models in these flows and operations. So how can a threat actor come around and abuse a certain parameter, a certain field, a certain flow? If you're not familiar with threat modeling, I just came from PyCon US, and Jason McDonald, dev relationships at WASP, shared all WASP cornucopia here. So it's a collection of cards you can use in your company to run various scenarios of threat models. I found for developers, this is a great way to raise awareness about threat modeling and vulnerabilities in our websites. So tackling security from the very beginning of the process is what I call security by design. It's also called shifting left security. And that's what we want to learn to do in this presentation. So instead of leaving security for the end, instead of doing design, implementation, deployment, testing, and then security at the end, we want to bake security at the beginning, from the design stage. We want to put those constraints. We want to redesign the flows and the operations in a way that we reduce or minimize the chances of those flows and operations being abused. Now, there's something very important we need here. I mentioned documentation. We need that. If we don't have accurately documented APIs, we can't really do security by design, because the design is reflected in that documentation, in that specification. So that's the first step. If we're going to start working on a new API, it's important that we do this design exercise and we reflect the design on a specification. If we already have an API in place and it's not accurately documented, the first step is to get that documentation in place as accurately as possible. Then we can run a spectral against the spec, and we can run validation tests against the backend, automated based on the spec. Now, what I've done over the past years is I've looked at tons of different public APIs at my clients as well. And I've been putting together a number of categories in the design space that relate to API security. We're going to look at some examples here. We can't look at all of them. But when you get access to the slides, you will see what they look like. The idea here is to get you familiar with what those vulnerabilities look like and how we tackle them. So we're going to begin with sequential IDs. We're all familiar with them. Sequential IDs are natively supported by most databases. They're very easy to work with, very easy to reason about. So if we have an issue with a specific resource, we just pass the number around and we can easily locate it in the database. The problem is when we expose those values directly through the API. Because they are sequential, they are predictable. And so something like this can happen, right? Imagine we have a payments API. We make a payment, we get back an identifier. We make a second payment, we get back a second identifier. We see a predictable pattern in those identifiers. So a threat actor may come around and say, well, what happens if I enumerate those resources? I start from number 1 and I go in a sequence all the way to number 2000 or something similar. We may have situations in which the constraints we have in place in our access controls are not sufficient. We may end up leaking some information, perhaps about existing resources or details around the resources that may show up in a stack trace or something like that. So there are real cases behind this also, like Clubhouse had a data breach in 2021, partly due to the use of sequential IDs. There were many more things coming together in this data breach. It was affecting 1.3 million users. So when you look at data breaches, when you analyze them, most of them are due to various factors, not just one category. And so what we have here is we have sequential IDs, we have lack of authentication against a sensitive endpoint like this one that is accessing user details. We have unlimited access to those endpoints. So, the fact that it is possible to send 1 million requests from a few machines or a single machine and not have those requests throttled or rate limited or flagged is an issue in itself. We have also excessive data exposure. This is an endpoint that can be accessed before establishing a trust relationship with the other user. So we are automatically accessing those personal details. We should be redesigning those flows so that we can only get access to that data when there is a trust relationship, for example. Of course, Clubhouse comes around and they say, this is not a breach, really. This is how the API is intended to be used. Of course, it's an API that is vulnerable by design, but that's not how we should be designing APIs. Now, how do we prevent these sequential IDs? Well, ideally, the best way is if we can use a different type of identifier in the database, something like UUIDs. That makes our life easier. If we can't, if we already have a database with existing sequential identifiers, or if that's a requirement, what we do is we use something like a hashing function or an encoding mechanism to hide the value of those identifiers, so that what we show to the users is something that looks random, but it is something that we can, in our system, we can decode and consistently correlate to our resources. So that was an easy one. Now let's go to something a little bit more complicated, like unbound parameters. So this is very related to what we discussed at the beginning, the pagination parameter. So unbound parameters are parameters that can go in a URL in the form of path or query parameters. They can go as well in a payload. And these are parameters that don't have constraints. So think of numbers, strings, and arrays. The problem with these unbound parameters is they open the door for different kinds of attacks. We saw before pagination attacks. There is also big integer attack, large payload attack, SQL injection, and many more. So this is the pagination pattern we saw before. We already saw what happens with per page. We can abuse that with requesting many items per page. The problem with that, of course, is going to put pressure on the database. And maybe one request won't do a lot of trouble, but if we send 1,000 requests at the same time, that's going to put a lot of pressure on our system. Now, the SQL injection that I showed you before wasn't too useful, but something like this will work if the queries are not parameterized in our implementation. So we could say, well, filter things by close quote or 101. So what happens is if we are doing string interpolation in our query, so we're going to put that string interpolation around 2 quote marks to include the value of that parameter in quote marks. So what we're going to do is we're going to close the quote mark, and we're going to say select everything from table X where the filter is an empty string or 101, or basically either is equal to this or yes, or return everything. Now, if that passes through, we may be able to override a lot of access controls on that endpoint, including user-based access controls. So like I said, in many cases, it might not be desirable to put any constraints on that parameter, but when we can, we should, and we can do it with enumerations, with regular expressions, and many other strategies. And by all means, we have to parameterize our queries. That we should never trust input coming from any source. What we can do also is resource starvation. So imagine we combine the page request of 100 million items per request, and we say, right, the filter is going to be what the string or say or 101 or something, and we inject also a sleep function. So that is going to hold the request with the database for 10 seconds or whatever we specify. What we can do is we send just a few of those requests, maybe 5, 10, 100. At some point, we may run out of the connection pool. All of those requests are waiting for the database to return, but also all the data is going to be holding memory. So at some point, the database server is going to run out of resources and it may just collapse. So these are some of the things we can do with those parameters. We can abuse this vulnerability in other ways as well. Imagine we have a book catalog and we can put reviews of the books. And so the expected request is we send our review for a book and we say, what's the rating? We write the review. And it comes back with a representation of that, including the ID of the review and how many votes we have. Now, we can abuse this in several ways if we don't have any constraints. So imagine the review schema looks like this. So we have rating, review, that's all. So we may say, well, send a rating of 500 and see what happens. We can push the score of the review higher. And we can also say, well, the upvotes is going to be set to 100 million from the beginning as well. If those values pass through, we're going to be able to abuse the review system of the website. What we can also do, imagine there is a book on the catalog. There is a competitor of my microservice APIs or secure APIs book, and I want to make sure this book is not loading. What I can do is I can set the text of the review to a huge payload, something extremely large, and that gets saved into the database. Now, one review is not a problem, but if I send 100 or a few hundreds of those, loading those records from the database is going to be painful, and at some point it may not be possible at all. I've seen this in some APIs. And so in this situation, we would just be unable to load the record. So how do we prevent these things? We want to put constraints in place. So for the rating, we want to have a minimum value and a maximum value. We don't want to be able to put, for example, negative values and affect those ratings in that way. For the review, we want to have a maximum number of characters. We don't want to allow people to put any kind of text in there. Something also we can use here in terms of OpenAPI specification, we can ban additional properties in the payloads by setting them to false. This means the original request we have here with upvotes won't pass. And we should validate that the same in the backend. So that's to prevent them. There are some other categories that I have here documented, but I want to move on to the testing section now so that we have some time for questions as well. And you can see the information in the slides when we share them. So to tackle this at a scale, we have to use automation. And so we need to look at testing strategies. If they won't capture everything, especially when it comes to business flows, those tools won't be able to understand your business logic. But there are some things we can capture, especially at the level of the design, at the level of the specification. So we can distinguish between testing at design time and testing at runtime. At design time is against the spec. At runtime is against the running server. So the tools I want to show you here are Schema Thesis for runtime testing and Spectral for design testing. Fensa is the one I'm building. Like I say, it's not very developed yet, so we're not going to spend time on that. So Schema Thesis validates our implementation against the spec. That's why I say it's important to have accurate documentation, because we can use it as an artifact for testing. And so what we do is a Python package. So we do pip install Schema Thesis, and then we run Schema Thesis against the specification. We give it the details of the server, the address. We can put some additional configuration if we want to use stateful links and what kind of checks we want to run. Stateful links is using OpenAPI links. So this is a way in OpenAPI to describe the relationship between endpoints. So we can say there is an endpoint here, which is a post, creates a resource, returns a resource ID, and we can replace that ID in a different request. I don't have more time to expand on this, but if you have questions, I'll clarify more later. Basically, Schema Thesis is gonna do this. It's gonna go endpoint by endpoint, and it's gonna check whether the endpoint behaves as described in the specification. So this is incredibly useful, because suddenly we can use the specification as a driving tool for security testing. Let's skip Fensa and go into Spectral. So Spectral is a linter. So it's going to check that the API documentation is correct, but it has a plugin for OWASP testing. Now, OWASP, a lot of OWASP is really more like business logic oriented, and it only can be captured at runtime. But we can capture some vulnerabilities at design time, and this plugin is going to look into those things. So install Spectral. It's built by Stoplight. It's an API company that was acquired recently by SmartBear. So we install Stoplight. We install the OWASP browser plugin. We include that configuration in our Spectral file, and we run Spectral against the spec. This is another example against an API that I had the chance to work with recently. We had about 300 problems we had to fix. And this is what I mentioned before: lack of constraints on integers, arrays, strings, and so on. And this is what the picture looks like more in the security space. So we have from hundreds to thousands of problems in most APIs, and these are potential problems that are in many cases not handled even in the implementation. So if you have an API out there of yours, what I recommend is wrap the specification. If you don't have the spec, put the specification in place. That's your first homework. Run Spectral against the spec, see how many potential vulnerabilities you have, and then use a Schema Thesis to see how well the implementation abides with the spec. And then you can drive security from the design by using the spec as an artifact in those analyses. This is just an example. When you get the slides, you will see an example of how to use a Spectral and a Schema Thesis in your continuous integration process. Here is an example with webhooks. And that's about me again. And that's all. I think we are on time. We have some time maybe for some questions. And thank you for listening. And that's all.
Great talk and great timing, Jose. If you wouldn't mind, can you go back to the discount for the pre-order on your book, so we can have that sit here while we go over a question or two?
Thank you.
We only have a couple minutes, so we could probably only get to one question. And so my question was back on your Clubhouse slide. We don't need to go to it, but I can summarize that. There seems to be a trend with some of these data leaks and data breaches that, they had the response that it was misleading and false.
Yeah.
I think Peloton had a similar treatment, Duolingo, and even Venmo, where it's like, lack of rate limiting, lack of authorization, yet, an attacker could come along and collect all this data. What do you think is going on there from, their perspective, and what should be done to fix it?
Well, I think we're not tackling design. We're not tackling security from by design. I think that's the problem, right? Think of Trello. Dan Barona had this conversation with Eric Wilder, right, about what happened to Trello. And it's a little bit the same situation. The API was just used as intended. It just wasn't designed to be secure by design. So we had the ability to query user profiles by just providing an email to the endpoint. It was unauthenticated. It was exposing too much data. There was no rate limiting. So I think what we have is this situation that a lot of the time we are designing APIs kind of organically. Like we need this new feature on our website. Let's put an endpoint. Hey, I need these two additional parameters on the data model. Let's put them. But we're not thinking about but what are the security consequences of that? Can we break down this flow into maybe 3 steps that we can use to track user behavior? For example, Taylor Swift, whenever there's a concert, all the tickets gone. It's too easy to bypass all the checkout process. Bots can do that, and there's no way of tracking that. Can we break down that checkout process into multiple steps and see, for example, how long it's taking from one step to the next? Is the user going in terms of milliseconds? Well, that doesn't look like a human. We can do something about it. And then we can put additional constraints, right? We can say, well, how many tickets can you buy in one go? Surely not a million or something like that. And we can check the origin of the requests, to track where they're coming from. I think that's not done in many cases. So I think it's a lot of it is designing the flows in a way that there are less chances we can abuse them, but also we can be better at tracking user interaction with the API.
Good talk and great advice. Thanks so much, Jose.